In these slides, we want to understand what EMF is for a closed loop of wire. If you have a closed loop of wire like this, and we want to see what the EMF means for that. So imagine you have the free charges inside the wire. These are some of the free charges. What could be done for this loop of wire to make a sustained current in the circuit? I mean by sustained current, a current that doesn't die out with time, that just keeps on going. Well, one way to make a current in the circuit, of course, is very easy. You put a battery, and the battery is to pump charges from one side to the other side. So it takes the negative charges from this side and puts them on this side. And what does that do? It creates surface charges that are not shown here. And these surface charges, negative on this side, and then they become positive on this side, they produce an electric field, a static electric field due to the static charges inside the wire. And that's what makes the charges in the rest of the wire experience a force, and they start to move, making a current. Remember this picture that we had before of a circuit and the surface charges that are on the surface of the wires, negative on this side and then positive on this side, and they were non-uniform so that they make an electric field inside the wire. Okay, another thing that can make a current in a circuit we just took is if you put a magnet, and you take a magnet and you move it towards the loop or away from the loop. Remember, we showed that this also can induce a current in the wire. And as long as you're moving the magnet towards the loop continuously at some certain rate, it'll continuously make a current in the wire. Of course, at some point it'll go through, then it'll go out, but in general you can keep a current sustained in the loop for a certain amount of time. What else could contribute to making a force on charges to make a current in the wire? You could have a mechanical force like a conveyor belt, like what they do in a Van de Graaff generator, which actually takes charges and the charges attached on the conveyor belt, and it actually rotates and it physically moves the charge from one side to the other side. So it's making a force on them, making a current in the circuit. It acts like a battery. It pumps charges from one side to the other side, which can make a current in the circuit. Now, in general, there are two. What kind of force would a charge feel that will make a current in the circuit? Would it be a parallel force to the wire or perpendicular force to the wire? If there's a force perpendicular to the wire, obviously it's not going to be responsible for making the current in the wire. So only the parallel component of the force is one that helps establish a current in the wire. So how could we pick out the component of the force? Force in general exists at some angle like this, theta, with respect to the wire at this location. How could we pick out only the part of the force that's along the wire? Well, if we define an element of length ds along the wire, and we get f dot ds, the dot product is f ds cosine theta. And f cosine theta is f parallel. F cosine theta is the component of the force parallel to the wire. So f dot ds is f parallel times ds. So these elements of length, you can make them go around, the ds vectors, you can make them go around clockwise or anti-clockwise, doesn't matter. But you have to just make one choice, and then you can get then the EMF. We're going to get the EMF going around in one particular direction. And you have to take what's happening at all parts of the wire, because you could have some part of the wire here where the force F dot ds is negative, and you could have some part here where F dot ds is positive. So here the negative charges are trying to be pulled this way, and here the negative charges are trying to be pulled this way. So they're trying to be pulled in opposite directions. So they could be creating currents, tendency to create currents in opposite directions. So that's why if you want to get the EMF, or to understand what's going on and if the current will be established in the circuit, you have to get the EMF around the closed loop, because different parts of the loop could be making forces in different directions. So how could we define a quantity that can take into consideration what's happening all over the circuit? That's where we come into this loop integral. You go around the whole loop and you integrate f dot ds, divide by the charge, and that's what the definition of EMF is. F dot ds is work. Divide by the charge, that means it's the work per unit charge. The word EMF is unfortunately used, electromotive force. It's not a force, right? EMF is not a force, it's work per unit charge. But somehow the name EMF has stuck, and so people keep on using the name EMF. So we'll just call it EMF, and we know that it's this. We don't have to say that it's electromotive force. We can just call it EMF and know that it's the work per unit charge going around the complete loop. So as we said, the EMF is equal to the work per unit charge as it goes around the complete. So if this integral is non-zero, then there's a reason that the charges will move in the circuit and you'll have a current established in the circuit. If this integral is zero, then there's no reason for a current to stay flowing in a circuit. There may be some temporary currents, but they will always die out with time. For instance, remember we said before, can a static electric field produce an EMF in a closed loop of wire? If you have a closed loop of wire, can you just apply a static electric field somehow and make a current, establish a current in this loop? Well, we did this before. We showed that the closed loop integral of E dot dr is zero, and we showed it by this way, by getting the potential difference between 2 points, which is this, and then now taking point 2, going all the way back to point 1 over loop. So the potential difference between these 2 points is 0. It's the same point, and so the closed loop integral of E dot dr is 0. Now if integration of E dot dr is 0, and if we just multiply up and down by q, then q times E is f, and q on the denominator is just q, and then that says that the EMF, integration of f dot dr over q, that's the EMF, right? It's the EMF due to the static charges. It's always 0. So a static electric field can never create an EMF that's sustained, that can sustain a current in a circuit. It can't produce an EMF. It's not a source of EMF. So when you have a battery like this, remember a battery pumps charges, and it makes charges accumulate on the surface, and those surface charges make the electric field inside the circuit. So yes, the thing that's making a force on the charges in the circuit is this static electric field, but it's not the source of the EMF. And there's a difference between these two things. It's true that this static electric field is the one that's making a force on the charges, that's why they move, but the static electric field is not a source of EMF in this closed loop, because when you take integration of F static over Q dot dr around the closed loop, it's always 0. So the static electric field on its own can't produce the current. If you take out the battery and you just put a wire here, everything will die out, the current will die out. The charges on the surface will just equalize, and the current will just go drop to 0. So the thing that was making the current and keeping it established in the circuit was the battery, by pumping charges. So the EMF is due to the battery, the other forces in the battery. That's the one that's making the EMF in the circuit. If you turn off the battery or just replace it by a wire, then all the charges will equalize and the current will stop. So the EMF is due to the other forces in the circuit, not due to the static electric field. Okay, so the EMF going around the closed loop, we can write it as integration of F dot ds over r, the work per unit charge. This term is useful when you're talking about electric or magnetic or mechanical forces. But if you're talking about a battery and other things like that, you have to include the EMF due to those things separately. But you can't talk in that case about a particular force. But you can find a way to write down the EMF due to those other things like the battery and any other kind of source of EMF. If you focus on electromagnetic forces, the electromagnetic forces that exist are the electric force and the magnetic force. So if you get F divided by Q, you get E plus V cross B. So this is then the origin of the EMF for electromagnetic forces, these two terms. And we can show that when the wires are fixed, this term actually won't contribute at all. We'll do that in the next video. But for now, we'll just say this is actually not going to contribute to the EMF when the wires are fixed. So the only thing that's making a contribution to the EMF is the electric field. And so if you define the EMF to be integration of F over Q dot ds around the closed loop, F over Q, when you're talking about electromagnetic forces only, we don't have any batteries, we don't have anything, we just have electromagnetic forces. The V cross B term doesn't contribute, and only the electric field contributes. And so the and in this case, for a fixed wire, is just integration of E dot ds. And integration of E dot ds, of course, we know that's 0 for static charges. So that's not the conservative electric field due to static charges is not the origin of the EMF. It has to be due to a change in magnetic flux. So we can then write, remember we have this equation that integration of E non-conservative dot ds is minus d phi by dt. Well, now we know that the EMF is also equal to this for when the wires are fixed. So we have just an extension of what we had before. We can just say that what we had before, integration of E dot ds, the non-conservative electric field dot ds, due to the change in magnetic flux, this is just equal to the EMF around the closed loop. And so now we have a relationship that relates the EMF in the closed loop to the rate of change of magnetic flux through the loop, and the electric field, the non-conservative electric field that's created going around the loop. And this equation, again, it's only valid if the wires are not moving. If the wires are moving, then other things, we can't really say that this is equal to this. So we have to rewrite things slightly differently. And we'll do that later in a different part of the chapter.